So let's look at two different types of waves. There are transverse waves and there are longitudinal waves. I got backup pencils. So there are two common types of waves that differ because of the direction in which the medium vibrates compared to the direction of travel. There are longitudinal waves and there are transverse waves. So, yes. So longitudinal waves are going to be in the direction of their length. This would be like air. Air goes forward, then backward, then forward, and backward. Transverse waves vibrate up and down while they move, like water waves. Cody, you're messing. Everyone good? No. Does everyone know what the word medium is? Put on your mask, Michael. A medium is whatever material you're going through. So, for example, if you throw a pebble through air, the medium it's traveling through is air. If you throw it underwater, the medium it's traveling through is water. Medium just refers to whatever material an object is going through. So, for example, when we're talking, the sound wave is going through air, so the medium is air. If you were to try to scream underwater, the medium that the sound wave is traveling through would be water. If you scream through a door, the sound wave will go through air, then hit the door, then it'll travel through the door material. Mm-hmm. Mm-hmm. Yes, and then the air bubbles will float up too because they're lighter. If you're blowing out, you're not breathing in. And go to your mask. It'd be difficult, but you could theoretically. You would breathe in a lot of water. But you'd breathe in a lot of water too. So a transverse wave is a medium that vibrates perpendicular to the direction of energy transfer. So in the direction that the wave is moving, a transverse wave vibrates perpendicular. This is a side-to-side movement. This is what we normally think of when we think of a wave. So vibrations of a string instrument such as guitar, radio waves, light waves, S waves that travel through the ground. By the way, an earthquake, if you didn't know this, there's two components of an earthquake. It has both transverse waves and longitudinal waves. This S wave is known as secondary or shear wave. Yeah. Yeah, I'm going to. So whenever an earthquake happens, so it's known as the secondary or shear or S wave. It's the upward. I'll put it back in there for a second. It's the up and down motion. So if you were standing on the ground during an earthquake, you'll be vibrating up and down due to the S wave. This is where you see the roads start buckling. So during an earthquake, this up and down vibrations is the S wave. So as the earthquake moves out, some of the ground is going to go up, some of the ground is going to go down. This is going to be the S wave. So we see here, so an earthquake was started here, and we see the ground start vibrating up and down, and we see this wave propagate outward from that source. Again, the S wave is going, so the wave is moving in this direction, moving to the right, and we can see that the particles are moving perpendicular or up and down while the wave is moving horizontal. So if it's moving horizontal, this wave is moving horizontal. The S wave or the transverse wave will be up and down. Perpendicular. That's because of the delayed motion of your eyes, but so you can finish writing this if you didn't get it. Thomas, put your mask on properly. I just explained that. Did you finish? Is everyone done with this? Guys, y'all quit talking. If we get done with this quick, I'll put on a Kahoot. Yes. That's what I'm going to get into the other. I told you there's two different ways. So is everyone done now? Alright, so again, to go back and explain it, there are S waves. The S wave is called a secondary wave or shear wave. It's the motion that causes the ground to move up and down. So again, if we have an earthquake being generated here, we would see the ground start going up, shaking up and down, and it's perpendicular. So that's a shear wave or a transverse wave. As the wave is moving along the surface, the ground is going perpendicular to this direction the wave is moving. So again, if the wave's moving in this direction, a transverse wave is perpendicular. It makes right angles to it. So it's called a secondary slow wave. Just secondary or shear or just S. So the distance between adjacent peaks in the direction of travel for a transverse wave is called what? So what is the distance between adjacent peaks? Yes. So the distance between two crests are called a wavelength. So it's the distance between two adjacent troughs or two identical portions. So the vibrations along a transverse wave move in what direction? Yes. The vibrations in a longitudinal. We'll go longitudinal a bit. The vibrations are perpendicular for a transverse wave. Now let's look at longitudinal. Longitudinal, the medium vibrates parallel to the direction of energy transfer. They move backward and forward movement. They consist of compressions and rarefactions. So instead of having a crest and a trough, we have a compression and a rarefaction. So examples of longitudinal waves would be sound waves. Sound waves is the number one longitudinal wave that you encounter. I'm going to show you a very nice picture of a longitudinal wave once everyone gets done writing this. Everyone done? Keep the mask on us. So here's a picture of a longitudinal wave. So we're generating sound. We see that the air molecules are going to bunch up together, and some portions are going to separate apart. So in a longitudinal wave, the air is going to move in the same direction as the wave, and they'll collide and bunch up. They'll also pull apart. So during a longitudinal wave, the particles move in parallel to the motion. And this would be an example of a P wave, or primary wave. The primary component of an earthquake, how it travels through the ground. We also get S waves too. That's the ones we mostly feel. So there's two types of waves with an earthquake. I'm doing it. Everyone done? So here's an animation. So here's a wave. Here's a single compression moving along. So here's a compression moving along. If we were to look at a single particle, the particle is just vibrating back and forth. The wave, or it's not called a crest in a longitudinal, it's called a compression. The compression is moving in the same direction. The individual particles are moving parallel. Again, remember, waves don't cause matter to move far distances. They only vibrate back and forth. So a single particle will only vibrate back and forth in either wave. So even though it looks like all these particles are moving along, they're not. Any individual particle is just vibrating back and forth. So this would be like sound. Let's see if... So here's another example. This is a longitudinal wave. We see that there's a single compression. So it's a really bunched up energy. But look at the spring. The spring's just vibrating back and forth. So we watch this. It moves, then it bounces back. So this part of the wave, the spring is not moving, but the wave itself, or energy, is moving with it. So this is a compression. This is a rarefaction. So let's look back at earthquakes. So during an earthquake, we have S waves, but we also have something called P waves, or primary waves. So this would be primary, or P. So it's where it bunches up on each other.
Okay, so like there would be the regular aspect and then what about the
It's a combination of both, but they travel at different speeds. Yes. The S waves, let's see, let me Google that, I don't know. Which arise first? P wave or S wave? Not off the top of my head. P waves travel the fastest. I could have guessed, but I didn't want to be wrong. I don't make mistakes, and I was only 99% sure. There's a 1% chance of failure, and I don't make failures. So P waves travel the fastest and are first to arrive in an earthquake. Shear waves, so the vertical motion comes later. You learn from your mistakes. So here's a side by side of it. So this is a transverse wave. Notice how it's going perpendicular. And this is a longitudinal wave. So there are two different types of waves. Now then, how can we figure out the wavelength of a longitudinal wave? Again, we can look at any two identical portions. So we can look at the distance from one compression to the other compression as a wavelength. We can also look at the distance between one rarefaction and another adjacent one, and that'd also be a wavelength. So the wavelength of a longitudinal wave, it can be either two successive compressions or two successive rarefactions. So the wavelength of a longitudinal wave is the distance between two compressions. Yes. Thomas. Cody. Your mask. So there are something known as wave interference. It occurs when two or more waves interact with each other because they occur in the same place at the same time. Superposition principle says that the displacement due to the interference of waves is determined by adding the disturbances together. Basically what this says is that if two waves were to meet, they will interfere with each other. And the superposition principle states that they'll just add together. Cody. Michael. So, there are two types of interferences, constructive and deconstructive. When the crest of one wave overlaps the crest of another wave, their individual effects will add together to produce a wave of increased amplitude. So they'll come together and make a bigger wave. Yes. When a crest of one wave overlaps the trough of another wave, the high part simply fills the low part, and so the effects are reduced or canceled out. Yes. Yep. Yes. So this is how active noise canceling headphones work. Is they have little speakers inside of them, and they have a microphone on the outside. Whenever sound comes in, it plays a destructive wave into your ears, and so that the wave outside and the wave inside the head cancel each other out, and you can't hear anything. Maybe, yeah. So that means that if two people were talking and the waves were perfectly out of sync, you wouldn't be able to hear anything.
Oh my god. No, I'm having to do it. Like, you have all of that. I read the house that I was in town.
So we can see the interference pattern when two waves of vibrating touch a surface. The regions where the crest of one wave overlaps the trough of another produces zero amplitude regions. You don't really need to write this down. But look here. We have, guys, we have 2 points vibrating, and where the crest of one and the trough of the other hit, we can see these calm patches. And where the crest of one and the crest of the other hit, we see it's really bright and hits up. What? Yeah. Oh, yeah. So let's look at standing waves. So if we tie a rope to a wall and shake the 3 ends up and down, we can produce a train of waves. I'll review this later. I want to show y'all a video. So whenever, guys, pay attention. Whenever you shake a rope that's attached to a wall, the wave is going to hit the wall and reflect backwards. So if we look here, so we send this rope, this wave down, hits this wall, and when it hits the wall, it's going to bounce backward. And as you continually keep adding more waves, they'll keep bouncing backward. And what we have is 2 waves hitting each other. And Michael? Yes. So these points where it's not vibrating is called nodes, and the point where it vibrates the most is called antinodes. So because the wave is reflecting backwards, it creates a reflected wave, and you have the wave you're generating going forward. And they're going to add together. So, alright, so this is a wave generator. So this thing's vibrating back and forth. So this thing's moving back and forth, so we see waves being produced. They're not very strong. They're going to hit this portion and then start bouncing backward. So now they're moving backward. And the two waves are adding together. We have a crest hitting a crest. And then they're going to get stronger and stronger and stronger. Note that it's the same wave. He didn't increase the wave. It's just two waves adding together. This reflected wave is coming back. I wish it was higher resolution. So again, this is a standing wave. And it appears to be standing still. I have a device that will make a standing wave and rope. We won't do it with water, we'll do it with a rope. Don't have time. No, we don't have time, we'll do it next week.
Okay, for this demonstration, admire stand my hand up and down, and you'll see that the little bump in the spring travels from me to Parker and then back to me again. And you'll notice that is perpendicular to the direction of propagation of the wave. So I'll move my hand up and down, and you'll see that the little bump.
So you notice the wave goes here, hits his hand, and bounces backward.
In the spring, travels from me to Parker, and then back to me again. And you'll notice that when the wave hits Parker's hands, because he's holding it firmly, what was a peak heading toward him converts itself into a valley as it bounces off of his hands.
And Michael, put on your mask.
So then a standing wave is where you pick a frequency that matches the length of the string in such a way that the waves created from my side of the string and bouncing off of Parker's coincide with each other and reinforce each other to create a standing wave pattern. The lowest frequency standing wave pattern is this one. It's called mode, M-O-D-E 1, or the first harmonic, or in other words, also called the fundamental mode. It's the lowest frequency mode that you can.
So the wave is going over here, hitting this, coming back down, and they're interfering with each other
in a transverse
in such a way
standing
that we get
wave.
a very.
If I double the frequency of that mode, I get the second harmonic.
So again, the wave is coming around here, hitting this, and then bouncing back like this. And then he's doing it at the same time, so that he's producing a wave moving to the right, and then the wave reflecting back to the left. So there's two waves. So the wave he's generating, and the wave reflecting off, and they're
second mode.
They're interfering to make
called
it
the first overtone. And this one, if you'll notice, is going twice as fast
And this is called a
And
node right here. It's where it's not moving much. He has a node in his hand and a node over
is
here.
the fundamental mode. It has a node that's exactly halfway between Parker and me. And that's a node where...
So here he's going to be trying to generate the third one.
Let me try again.
So we can see right now he matched
Okay, I
perfect
think
speed.
I've got it approximately now. I think I had it for a little while there. That's the
It's
third
kind of
mode,
hard to generate by hand.
where the string vibrates in 3 separate segments. There's actually an infinite. I think that's 4. And then if you're really, really good, you can get 5, 6.
So what we have here is a frequency generator. It's connected to what's called a wave driver.
So here's
Old frequency. Let me just turn this on.
so it's just vibrating this point up and down.
So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a stand.
So the wave is going down here, hitting this, bouncing off, coming back. But he's doing 2 waves. There's a reflected wave and the wave he's generating, and they're colliding with each other.
That is the wave that's sent down. And so the node is not moving.
So let's look at it in slow motion.
So here we have what's called the second. So we have 3 notes for this wave. Now, like I said, second harmonic. Well, what's the first one? The first one will be half this number, so 8.5.
So there's, yeah.
And there we go.
Yeah, there's a node on both sides.
It's basically the scenario. That's the third harmonic. 3 times 8.5.
Yeah. So he's going to increase the frequency. And then notice that when he gets it very constructive, the crests are going to, or the amplitude is going to increase.
So that's the third harmonic. How many wavelengths is this? Well, and it's easier to see in high speeds. 1 1/2 wavelengths.
So again, you see a wave. So here's a full wave, just this portion. And then here's half a wave. It's going to hit, and then it's going to bounce back. And this wave, so this wave is going to generate, yes. So we see a wave being generated like this in this direction. And then it's going to come over here and hit this wall. Then the wave is going to bounce off the wall and come down here. But at the exact same time, he's going to generate another wave that's going to come over here and then hit like this. So that the reflected wave and this new wave collide right here, and it's going to make this get bigger. And eventually, this wave is going to hit this wall and reflect off of it coming this way. At the same time, his new wave will come around here and hit right here, causing the amplitude to get bigger. So he's sending waves, and waves are reflecting off. We can see that this wave will reflect down here, which causes the wave that he generates right here to hit right here and collide. Also, this reflected on the bottom is going to come back up and hit right here whenever this wave comes up, and at the exact same time, they both collide right here. And because it's a crest and a crest, it's going to get bigger and bigger. I do have a standing wave generator that we'll play with next week.
So again, third harmonic, 1.5 wavelengths. Well, let's go. Wavelengths.
So we can see here one wave right here, and then another wave, and then another wave. So there is 1, 2, 3 waves. There is 1, 2, 3, 4, 5, 6, 7 nodes. And these highest portions are called antinodes. So there's 1, 2, 3, 4, 5, 6 antinodes and 7 nodes.
And in the next video, the explanation video, we'll go through
the slow motion of that. And to answer your question earlier, Michael, in picture math, why the pin appears to be moving, bending, is because right here it looks like this is double. Because of our persistence of vision, we kind of see like an after image, so it's kind of lagged behind. It kind of looks like there's 2 ropes here. It's not. If we slow it down, we see that there's still just one rope moving up and down. Yeah, you're seeing it in its old position. So nodes are the regions of minimum or zero displacement, or with minimum or zero energy. Antinodes are the region of maximum displacement or maximum energy. And here we can see the reflected is dashed. In music, we call that a tune whenever we hear a standing wave or a note. So another illustration, note that this wave is moving. So this wave is going to move over. And we can see here, whenever it moves over, by the time this reflected wave comes back, it'll interfere. So we can see that this wave is moving. And the reflected or dashed line is moving in the opposite direction.